Hello everyone, I am Manognya and I am the head of Women in Computer Science at IIT Madras. So today we have Sowmya Sundaram with us. She completed her master's and PhD degree from IIT Madras and is currently pursuing her postdoctoral research at L3S Research Center in Germany. Um, she's currently working at the intersection of NLP and bioinformatics. Hi Soumya.
Hi,
Soumya, it's an honor for us to have you with us today. So you can start whenever you're ready.
thank you, Manongya. It's nice to be invited here. So, today I will be talking about an high level intro to natural language processing. So, let's get started right away. So, the idea in this presentation is to talk about what natural language processing is, what are the basic concepts, and it's not going to be a technical talk at all. It's going to be a very bird's eye view kind of treatment, and we'll go step by step and see what makes this exciting and interesting, and why research is uh, currently happening at a fast rate in this area. So let me begin with what is intelligence. The reason I'm starting with this, of course, is that NLP or natural language processing is a subset of artificial intelligence. And for that, we will briefly examine what are the characteristics of intelligence and what constitutes intelligent programming. As we all know, a computer program is something where we have a particular input and we're going to process it to get an output. But there is something that differentiates an AI program from a normal program. Usually, this is of course not a standard definition or anything like that, but we say intelligence has some of these components. One is representation. We need to represent a lot of concepts about our knowledge. The next is reasoning with these concepts. So, for example, if I have a concept like an apple and a concept as an orange, then the reasoning aspect could be something like both of these are fruits. So, how do I represent these kinds of information in a programmatic way? It's quite interesting to note that the object oriented paradigm uh, came from the research done in AI for representation and reasoning, and inheritance hierarchies were first introduced much earlier than when OOP concepts came into play. Now, this is on one side. Next, we have the action and perception idea, which is where robotics plays a part, where perception is seeing or deliberating with the use of senses, and action is taking a particular response to the stimulus. Now, a fundamental characteristic of intelligence is language. Language is the most important thing that has helped human beings evolve to such a great extent. And we don't actually understand completely how we communicate using language and how our brain processes language, which is what makes this field extremely interesting. So, this is a high level overview of what is AI and what are the various areas in it. So, in artificial intelligence, traditionally, we saw a kind of problem solving approach where we search through a number of solutions and choose the best one. Knowledge representation refers to what I was talking about, representing different concepts such that it is both useful for the machine and for the human user at the end. Then you have automated reasoning. Then, of course, you have the highly popular machine learning algorithms. And it is in this perceiving and acting domain we have the area of natural language processing. Now, coming to AI, this is, of course, a very famous test that many of you would be knowing, which is the Turing test. The Turing test basically says whether the particular aspect is a program or a human. So, a human will be testing whether what they are seeing on the screen is being generated by a computer or a human. Now, this aspect of artificial intelligence is known as acting humanly, where you want to somehow convince the human that, look, I am as good as a human being. Now, this has been done for many years. There's an international prize for this annually. And a few years back, the Turing test was passed, but that does not mean it was so good that it fooled everyone. The criteria was 33% of the audience felt that the program was not a program, actually. So, this is to give an idea about the level of complexity required. And incidentally, the Turing test competition that is being held is also a natural language processing task because you're basically going to be seeing chats on the screen. And initially, it was very easy to find out because if you ask some question like, what is the 20th root of a large number? And if the program were to answer that, you know it is not a human. So these are the kind of interesting challenges that language processing has. So, coming to that, let's first talk about the characteristics of language before we proceed to how computers process language. So, we have broadly have two kinds of languages. One is the machine language, where initially we had to go with binary and then it became simpler with the use of assembly language, and then we have programming languages. Now, the term natural language refers to languages that we use in our day to day lives, such as English, Hindi, Tamil, Bengali, and so on, so French, German, whatever. So you can see that we have a large number of diverse languages, each with their unique ideas and processes. Now, given the complexity of language, how do computers process that? So that is the area of natural language processing. So here it lies at the intersection of both computer science and linguistics. Linguists analyze how languages evolve, how languages are being used currently, and this linguistic information is being coded using computer science. And right now the paradigm is heavily in the deep learning domain, and we'll be seeing intuitions about the same in the coming slides. So let's start with what makes natural language processing hard, which gives us a motivation and an idea why this is very difficult. In fact, one of the AI scientists termed natural language processing as an AI complete problem. She said that just like how we have NP complete as a theoretical concept, natural language understanding or processing is an AI complete problem. This is because one thing we have to deal with is context. So, a very common example in on NLP textbooks is how do you differentiate between Bank of America and a river bank? So, this context understanding involves that we cannot look at a word as it is and we need to look at the whole sentence. Now, sometimes you might have to look at the entire text, not just a sentence. So, where do we stop? How do we process this? So, this is one major challenge. The second challenge is common sense reasoning. Now we know that you have things like she hit the ball, it went somewhere. You know that it refers to the ball because we have a set of rules in our head how the language functions. So these kind of common sense ideas are quite difficult to capture and uh, make it in a machine friendly manner. The next one is disambiguation, an example I had already told. And it's not just disambiguating based on word, sometimes it's even the meaning. Sometimes um, you have different words which mean the same, like synonymy or antonymy, which is opposites, and so on. How do we encapture all types of knowledge? So, in this regard, there was a massive effort known as WordNet, which had a set of hierarchies, ideas, definitions, which tried to handle this uh, difficulty in a way. So, you can think of WordNet as basically a dictionary. Next, we have co reference resolution, which is basically telling this part of the sentence is referred to in another sentence. So when we read a piece of text, we need to make these kind of connections to make sense of it. The last we have syntax and semantics. The way language evolves, the meaning of the word is not contained in the individual letters. It is often, it takes us quite some time to get the meaning of various words and place it in a linguistic context. So, syntax and semantics are very different in natural language, and that makes it quite challenging. So, with that background, let's get into how natural language in artificial intelligence is being handled. Broadly, there are two categories: natural language understanding and natural language generation. By understanding, I mean that given text in English to me, like say the boy sat on the grass, how do I process it from the computer's perspective? The other side of it is natural language generation, where I have a set of, say, sensor inputs that I want to generate in the form of text. We'll see a few examples to make this clearer. We have a lot of exciting applications of both understanding and generation. So let's say that our personal assistants like Siri, Alexa, and Cortana, etc., they are actually speech processing algorithms, but after processing speech, they do have to decode the language instructions. So these assistants undergo the natural language understanding paradigm. Then we have now ubiquitous autocomplete features where you have where we basically type a few words and it predicts the next word. We have spell checking, machine translation, where we have used Google Translate a lot, especially when we go abroad and things. Sentiment analysis is a task where you find out, given a piece of text, whether it has a positive sentiment or a negative sentiment. In the sense, say, movie reviews. Is the review positive or negative? So, an automated way of doing this often gives us a quick feel of how the movie did. Finally, we have question answering, where you need to understand the question and generate the answer, which is why question answering also comes in the generation aspect. Right now, on the generation side, chatbots are very famous. Many of the mundane tasks that humans have to do have been automated by chatbots to a large extent successfully in the industry. Then we have automatic summarization, where given a text, we generate a summary. There are two kinds of summaries, abstractive and extractive, where extractive summary basically means I choose a few sentences from the text and make the summary. And abstractive summarization means that I actually generate new sentences that are not there in the um, text. Then we have weather report generation, which is something that has had a lot of research done, but still it's quite hard to generate a report that is human friendly, because a weather report has a lot of numerical information, and to concisely summarize that and give a prediction and then generate it in text is quite a hard thing to do. Now we'll come into some of the AI aspects of natural language processing. The first and foremost thing is, throughout this presentation, we will be seeing how text is represented for machines. So here the role of representation is pivotal to natural language processing. What I mean by this is, say the number 2020. We can represent it in Indo-Arabic style or in the Roman style. But you can imagine the Roman style of numerical representation went out of vogue because it's quite hard to do addition, subtraction. It's quite hard to express numbers that are quite large. And that is why the concept of zero and position values in the decimal system made these numerals extremely easy and amenable for algorithms. So we will be seeing how algorithms have evolved over time for text processing, how we have moved towards better and better representations, what are the advantages and disadvantages of all these representations, and then we'll have some intuitions about the state of the art algorithms at present. So, in all AI paradigms, there are three major uh, classifications: symbolic AI, statistical machine learning, and deep learning. We'll be seeing how text evolved in each of these buckets. The first one is symbolic AI, where the human spends a lot of effort deciding how to represent language, what are the pertinent features of the language, and then process it and give rules. So, in today's parlance, it could just be a bunch of if else rules, a long list of rules, or things more complicated than that. But this is a general idea. So, a classic example of this is the very first chatbot, Eliza, where if you see, it basically just shifted a few words here and there to give you an illusion of a chatting robot. So here it says, hello, I am Eliza. Hello, Eliza. Yes, ask me questions. How are you? I am fine. Thanks for asking. Now, this is generated with a few rules, like if you see how are you, then give this, either that, or sometimes it just randomly generates a few outputs. It's quite a small program, but it was very convincing and very popular at the time it came out. In fact, the secretary of the scientists who developed it could not believe it was a program, because the human imagination is so powerful, and it was very cathartic because this is a very good listener. It will just repeat the sentences that have been posed to it in a different way, which makes it sound very understanding and empathetic if you think about it. So, behind the scenes in symbolic AI, the concept of grammars was used. So, by this, I mean that there were a bunch of rules stating how language is modeled. For example, it would say that the sentence is consisting of the noun and a verb phrase. So, John hit the ball. Here, John is the noun, and hit the ball is the verb phrase. Now, this means that it's also compositional. So, the verb phrase in itself consists of a verb and a noun phrase, which is hit and the ball. Again, the noun phrase consists of the determiner and a noun. So, using a small set of rules, the entire language is being modeled. And this is powerful in the sense it can be used for both understanding and generation. Given a sentence, understanding can be performed by constructing the tree, and then given few words, generation can be done as well. So, this was the high level idea, and it was very popular in the symbolic AI paradigm. Now, with this, however, scientists felt that the semantics have gone for a toss. Here, the syntax has been captured perfectly. We understand which is a noun, which is a verb, etc. But whether it is John, or whether it is a cat, or whether it is a table, there is no way to differentiate between the various sentences. So, in the symbolic AI paradigm, Roger Shine came up with an approach telling that if we are in a world such as the restaurant, then certain sentences have certain expectations, and we have to fill these expectations. So, this was a long, almost 10-year project where we saw how certain semantics give meaning and how to generate question answers for that. So, this was the symbolic AI paradigm. We next come to the machine learning approaches. Now, in the machine learning approaches, the idea is we have a lot of data, and how we are going to use the data to do this kind of natural language processing. So, at the outset, this is the idea. In a traditional programming setup, you have some data, you give a program, and you get the output. Say I have a program to find the square of a number. So I'll give the number 2, I'll give the program which says multiply the input by itself, and then I'll get the output 4. In a machine learning setup, on the other hand, what I'm trying to do is I'll be giving a set of numbers, say 1, 1, 1, 2, 4, 3, 9. So the data will be 1, 2, 3, and the output will be 1, 4, 9. And my program will guess that looking at this data, it's probably the square of the number. So this is the intuition behind machine learning. So how does it quote unquote learn? Basically sees the data points in your data set and tries to fit the closest function to it. Now, theoretically, this seems quite interesting and feasible, but the problem is we don't know the characterization of the underlying function. Is it a polynomial? Is it a circle? Or is it something more complex? What is the dimensionality? There are many concepts that are at stake. Sometimes you might make this curve perfectly fit every point, but then when it sees new data, it would not be valid. So at the outset, this is what machine learning does. It looks at a bunch of data and decide what model to be used. And we'll see how natural language dealt with machine learning and how processing was done. So in machine learning for text, first what we do is we have to convert it to a numerical framework. For that, we convert the text to a vector using predefined rules. By predefined rules, I mean that the human imparts some domain knowledge and says, convert this text to this vectorial format. In this manner, it is up to the human to find out an effective representation for the text. Now, after that, it is also important to change the output to a set of numbers. So, um, yeah, we'll see an example of that. Then the idea is finally to use a set of standard algorithms to predict the output given the input. Now let's take the example of sentiment analysis. A very naive approach is to use a vector and say if the word good is there, put 1. If the word good is not there, put 0. If the word bad is there, put 1. If the word bad is not there, 0. So you have a feature space of 2 vectors and then you go ahead. Now again, and your sentiment is basically 0 or 1. Of course, in this case, you might just say, I might as well put if else good or bad. In reality, you'd have a lot of other features. This is just a toy example. So the idea is in symbolic AI, though a human expert invested a lot of effort into modeling the language, they were able to see that the result was not great. It was not generalizing well. If the rules were applicable, the accuracy was 100%. But very rarely was a rule applicable. And that was the bottleneck. How do we select rules such that natural language processing is generalizable in future? So this led to the great Chomsky versus Novick debate when it came to symbolic AI versus machine learning. So Chomsky approach, this is not for language, this is for some other domain, but the approach is the same. So in the Chomsky paradigm, you go from the theory and you see how the data is behaving according to the theory. In the sense you have set of grammars or say the Shank story script, so on and so forth, and then you fit data for that. In the Norvig style or the machine learning style, what we do is we use the data to find what are the pertinent rules. The human does not figure out what are the rules. However, we saw that the human has to put some effort into changing it into a vectorial representation. And sometimes that might involve annotating the text. By annotation, I mean you might have to give some intermediate notation, or you might have to annotate the text with the output. What is the required output? At the minimum, you need to do that. So, at the end of this discussion, this is what an apple would look like in the symbolic frame and in the connectionist frame. Connectionist is a word referring to neural networks, where we say that we try to model how our brain works. And yeah, so for the purpose of this talk, just take it as yet another machine learning algorithm. And a symbolic AI, for example, would have a lot of information, such as it has an origin in the apple tree, it is a kind of fruit, etc. A connectionist apple basically says, I have this machine learning model and I have certain weights here and there. And all of these suggest that probably the input is an apple. So this is the major difference between symbolic AI and machine learning. Now we come to deep learning. What differentiates machine learning and deep learning? So, in some sense, deep learning is driven by neural networks and it is actually just a very large neural network. But the huge advantage that deep learning possesses are on two fronts. One is that the manual configuration of a vector suitable for the domain is no longer required. So the network itself extracts what features are important or unimportant. The second advantage is that there is now an explosion of data thanks to the way internet has been growing, and there's also a huge increase in the processing capabilities of computers. You might be surprised to know that the algorithms that were responsible for making deep learning possible, such as the perceptron, came out all the way in 1946, and the deep learning algorithms were present in the literature right from 2000s, but it was in 2010s we started seeing a large resurgence in deep learning algorithms. And we'll be seeing the intuitions behind many deep learning algorithms right now. Before that, I just have a small uh, thought bite, which is basically how did we as humans learn languages? So these are two pictures. This is the Tower of Babel, which is a biblical story, which says how languages evolved, and said that initially all human beings were speaking a single language, and then in the Tower of Babel, different languages evolved. Similarly, this is a Vedic goddess who is supposed to be the origin of speech. It's not goddess Saraswati, it's a predecessor. But generally, the reason I put this is that the origin of language has been quite fascinating to humans. How did we develop such a sophistication in communication? And if we think about it, as children, we did not learn complicated grammars to understand language. We did not imbibe a lot of common sense information to learn language. So, does that mean that a data driven approach is better? The answer is that we are not very sure because, on one hand, data driven seems more intuitive since we have not learned such grammars in depth. But the second part is that we have still not understood the way our brain functions completely to conclude that yes, this is the paradigm. Though we have neural networks that are derived from how our brain functions, we will be saying the disadvantages of neural networks and how our brain is far more complex, and we have a long way to go in research. And that is why both symbolic aspects and data driven aspects have to be taken into account for modeling languages, and we'll be seeing how in future. So the story so far, first is we had AI driven approaches where it's really tedious and requires a lot of troubleshooting. The second, we have machine learning where it's difficult to program it, but it is still more generalizable than the AI approaches. And finally, we have the deep learning approaches, which are the most generalizable, but also the least precise among the three algorithms because it is completely data driven without human intervention. Now we have a good background, and I can now take you through the intuitions behind the state of the art algorithms. I have kept this completely non technical, but if you do have technical doubts, please keep asking in the comment section, and I'll be answering it in the end of the talk. So let's start with word representation. Now, initially, traditionally, words were represented as one hot vectors. What do I mean by one hot vectors? Basically, I have a vector size in the length of the vocabulary. So imagine I have only one sentence: dog likes a cat. So there are only four words in my vocabulary, and hence my vector length is going to be 4, and each position is going to say what is the word. So dog is going to be 1000, likes is going to be 0100, and so on. So this is a word representation for a machine learning approach. This is not the symbolic approach. We are talking basically about the differences between the machine learning and the deep learning approaches. So, what are the disadvantages of one hot vectors? First thing is they are high dimensional vectors. Imagine if you are representing all the articles in Wikipedia at a particular time point. The vocabulary would be huge and the vectors would be of an unimaginable dimensionality. And if you've already gone through machine learning courses, you would know the curse of dimensionality and how, as dimensions increases, our favorite machine learning algorithms do not scale well. The second problem is the vectors are sparse. So in this high dimension, only one of the dimensions is going to be 1 and everything else is going to be 0. So it's quite hard for the algorithms to learn something useful out of such sparse vectors. The third is on a semantic front, every word is equidistant from every other word. In the sense, all the words sort of form the basis of your dimensionality space. So, to give an example, the word duck is equidistant from bird, is equidistant from school also. Whereas you would like a vectorial representation such that the word duck and bird are quite close to each other in the vectorial space, and duck and school is further from each other. Because of these reasons, word representation in machine learning became unpopular. And it was preferred to have a domain expert to analyze what are the features in the uh, domain and then come up with a vector for that. So, this is why word representation was not done. Then, new ideas started emerging, and there is a concept which says that a word is known by the company it keeps. So, as a side effect of a completely different task, word representations were learned. In the deep learning approach, a model for predicting the next word was built using one hot vectors, and there was an intermediate vector that was embedded in this model that captured relevant aspects of semantics, basically on the context and the position of the word and its frequency in the dataset, and it was able to provide a lot of interesting semantic information. The first thing is that the length of the vector is fixed. It is not dependent on the vocabulary. Say, I can say a length of 50, a length of 100, a length of 300, but it will not be the unimaginable number that it was before. Next is we have semantic representation. So in this representation, now we find that king is closer to queen than a word like novel. And also there are many interesting things like king and queen are the distance between king and queen is the same as the distance between man and woman. The next is that the vector dimensions are fractional. It is no longer 0 and 1. So it is not sparse and there's a lot of information that can be gathered. And from an implementation point of view, the biggest advantage is you can train this once over a large data set and then use it as a lookup later. So, say I have this sentiment analysis idea. All I need to do is take the words and find what is the corresponding vector that has already been trained and then do a simple classification algorithm. I no longer need to look for words like good, bad, nice, etc., as required in the machine learning approaches. Next, we come to the sequence representation. First, we saw how to represent a single unit, the word. Now, we come to the sequence representation, which is the text. So, initially, to identify sequences, concatenation was tried, averaging was tried. You can imagine concatenating would involve again blowing up of the space. Averaging would mean would lead to loss of the order or sequence information, and hence there was now a need to come up with approaches such that pertinent aspects of the sequence are captured. So, in a sequence, there are two important aspects. One is the ordering. So, if I say cat chases the dog or the dog chases the cat, the order is important for the semantics. And the next is variability in length. In the sense, the word cat has only 3 letters, but say the word catch has 5 letters. but still they are words, still the sequences have common information, and so on. So we need to have a model such that it captures both the order and the fact that each word is going to vary in length. So for this particular purpose, different deep learning architectures were developed, such as the recurrent neural networks or the long short term memory neural networks, popularly known as RNN and LSTM. And at the high level, what an RNN does is basically sees the order of the words and also takes care of the variability. It takes care of both of these properties, and that's why it's commonly used for sequences. But it has a few mathematical disadvantages, which is why we moved on to the LS teams. And maybe we could have a separate lecture on these later on for those curious about the same. Now that there are deep learning architectures to capture various aspects of a sequence, the next step is to convert a sequence to another. And sequence to sequence are very diverse and dynamic architectures where you can use a similar architecture to perform a wide variety of tasks. One thing is, at the outset, what you're trying to do is convert a sequence to the other. It can be just converting text, so one text to another in the case of machine translation. It can even be converting video to text. And this is where the generalizability of deep learning is popular. Finally, we come to a few of the more recent concepts. One is attention. Attention basically was was developed to address the fact that not all parts of a sequence are important. Sometimes in machine translation, the verbs are inconsequential and you only need to pay attention to the nouns, for example, for some particular language. Here, you suggest that look at only these parts of the sentence. And once again, in the spirit of deep learning, we don't specify where to pay attention, but rather it is learned as part of the learning process. So this has led to the transformer where it again transforms from a sequence to sequence, but it doesn't use the traditional sequence algorithms. Instead, it uses a lot of layers of attention, which mimics the sequence process. Finally, I'll be giving the intuition behind BERT, which is the latest in the sense, maybe I think 2 years back, it came up with converting sequence in the transformer style. But instead of looking up the words as vectors, you use the model itself. So you have a model and you pass the text. The model is already trained and you get the corresponding vector values. Before, you just had a text file which said this word is this vector. Now you have a program where you pass the word and the sentence, and according to context, it comes up with the vectorial representation. And this has shown a lot of positive results for the natural language processing domain. So now we'll come to the implementation aspects. So imagine that, okay, you are not interested in doing research in NLP, but you will be using the products of NLP research for your industrial task. So you might want to figure out what is the part of speech, what is the noun, what is the verb, etc. You might want to figure out what is the subject or the object. So this can help you in, say, chatbot development. Then you might want to get the embeddings that are already trained by researchers, and you can use a tokenizer to separate the words from a sentence. And you might be surprised that sentence boundary detection is a field on its own. While it might seem that it's very easy to just figure out the full stop or an exclamation mark as the end of a sentence, but the fact is, in the case of language, you have so many complex end of sentences, you have full stops to denote decimals, and so on, which makes sentence boundary detection quite a hard task. You can also have named entity recognizers, which are already pre-trained to say which is a person, which is a place, etc. And these are some of the resources that are available for you to develop your applications. From research perspective, you have the site nlpprogress.com, which has the major results of each NLP task and how far we've come, the data sets, which in a very neat format. You might want to use TensorFlow, Keras, and PyTorch for your deep learning architectures. Of course, from the engineering perspective, also you can use this. So the idea is that here, um, where you would need to develop your own algorithms of deep learning is when you have a lot of data and you cannot use the off the shelf named entity recognizers. For example, for your industrial requirement, you might want to find an entity completely not trained before. Say you want to identify whether this word refers to a movie theater. If you are in that domain, then you have to train your own named entity recognizer. For that, these frameworks are useful. These are all open source frameworks, and you have a lot of tutorials online to get the hang of it. And if you're interested in studying NLP and what is the map behind it, then you need to cover these areas where you have some idea of Python coding and you have do a cursory reading of the foundational chapters of classical NLP. You have some idea of machine learning and deep learning, and then you take a course for deep learning for NLP, and then you're ready to go. So here we are coming to the end of the talk, and here I'll be talking about my research in my PhD, what I did. So I was working on question answering, which is basically taking a word problem and figuring out the answer. And my domain would be something like this, where it says John has 5 apples. He gave 2 to Mary. How many does he have now? We can say, even in this simple example, we need to say that he refers to John and not Mary. We need to say that 2 refers to apples, which is our co-reference resolution. And then we need to identify the sequence of events, that this was first and this is second. So this is some kind of temporal reasoning. And finally, we need to address that the mathematical intuition is that now he has 5 minus 2, 3. So there are layers of understanding involved in this process, which is why the state of the art still struggles with question answering and makes it very interesting. And during the course of my thesis, I saw this from all the 3 lenses of symbolic, machine learning, and deep learning, and could actually see what are the advantages and disadvantages, which I'll be presenting here. So, in a knowledge based style, what I did was to classify the type of word problems based on psychological literature. Then I'll identify the relevant information required for certain rules and then solve them. Now, the advantage of that is that it is completely in my control. So, I can even come up with a short description of how the solution was arrived at, and it is precise. But the disadvantage is that the rules I crafted would not generalize well. So it could even, I remember there was a data set that I generated rules, and in a new unseen data set, it could not solve even a single word problem. So there is a high rule making effort, and your returns are not great on that. But it is very interpretable, which is useful for, say, tutoring systems where you have decided what the word problems are and you are generating the solution on your own. Next, in data driven approaches, data was used to fill the information slots in some of the domain ideas, and this enhanced the results, but it was not interpretable. And the greatest advantage is data driven approaches give an idea of comparing algorithms. You have a definite data set, and as efforts are being done, you can identify whether, at least on this particular data set, a particular algorithm is better or not. Here, there is, however, a high annotation effort, but it is less than the rule making effort. Now, in deep architecture, what happens is I basically just look up the embedding and try to guess the answer directly, or at least the equation, which is intermediate. Now, the disadvantage is, of course, it is not interpretable, but it doesn't mean that it is not useful. In the sense, even though it is not interpretable, there are efforts to generate explanation based on some language modeling, which is quite interesting. And the disadvantage, of course, is that it depends on the quality of the data, the algorithm, and the machines available. And word problem solving is an area where the amount of data available is quite less. For the deep learning approach, I had to augment the data set and blow it up artificially to get some good results. So let's see what are the challenges in semantic understanding, even with deep learning. So let's say this is a word problem I have. Sally has 3 apples, John has 4 apples, Kathy has 5 apples more than Sally. How many apples do they have altogether? Typically, a machine learning or a deep learning algorithm will try to combine the numbers that are there in the word problem quickly together and form an equation. So it will come up with something like 3 plus 4 plus 5. But if you see the problem correctly, it says Kathy has 5 apples more than Sally. So the number 3 will be repeated twice. So these are kind of quirky situations that are not captured by machine learning algorithms well. And this is captured well by symbolic AI, but it's quite hard to generalize it. Similarly, in the second box, we have this word problem. Sally is 10 years older than Mary. In 6 years, she will be twice as old. How old are they now? Which gives us this equation. But if I just change one word, which is instead of saying that she will be twice as old, if I make it thrice as old, it becomes s minus 3m is 12. And the number 12 is not even present in the word problem. So this involves a certain level of deeper analysis that if I have in 6 years, then my equation involves adding 6 on many variables. And these are hard problems as of now, even with state of the art architectures. So this brings me to the interesting Chinese room experiment that has been touted as one of the drawbacks of natural language processing algorithms right from the 1960s. So the Chinese room experiment says that I have a person who has a dictionary and who says that if I pass in a Chinese sentence, I will look at the corresponding English sentence and push it out. Now, this person does this job for quite some time. But when he comes out, he has no idea what Chinese is. So, what this shows is that our algorithms are mimicking the process of pattern recognition and generation, but they're not actually understanding when you look at the challenges in semantic understanding. And this is where research is going to proceed in the deep learning space. Also, it requires a lot of theoretical backing to make it generalizable in future. So the road ahead is we need to incorporate a lot more semantics. We need to move towards interpretability. There's also this concept of catastrophic forgetting. In the sense, when I have a trained model and I introduce new data to it, it will completely forget the previous model. So if I see a picture of a dog and I've learned the concept of a dog, and if I see a picture of a cat, I will not forget what a dog is. But catastrophic forgetting has that problem in deep learning architecture. The last most important thing is fairness and ethics. Remember, in the beginning, I spoke about how the distance between king and queen was same as the distance between man and woman. But a lot of problematic inferences were also done. Like the difference between man and woman was the same difference between doctor and nurse, which sort of assumes that women can't be doctors or men can't be nurses. And this is because inherently human data is flawed and biased. And if we are going to depend on this kind of language for all our algorithms, then we need to focus on removing bias. And this is a very active field of research at the moment. And with this, we see that we as humans have to introduce certain measures to fight unethical practices. And I think recently one multinational company stopped using AI algorithms to filter out resumes for this express purpose. So, yeah, I have come to the end of my talk. We can connect on Twitter and my website, which is available. And I'll now look, if you have any questions, you can put in the comment sections and I will be answering them now. So, thank you. And let's start with the questions. So, yeah, let's see. So I have a question. In case of representing words as vectors, the size of the vectors was fixed. But how do we represent sentences as vectors as each sentence may vary in length? So that's what I was saying. Representing sentences as vectors involves a concept like padding. So what we do is we assume that most sentences will not exceed, say, a length of 50. Then I'll have first few as the embeddings for each of the words, and then the last will be some stop character. So that's how we go about that. You also have another question. Can we use a vector whose size is fixed, equal to the size of a vocabulary, and then set the elements in the vector corresponding to the words in the sentences as 1 and remaining 0? That leads to the same problem as our one hot encoding. So instead, what we do is we use the word embeddings which are which are dense, which have the fractional values, and then we concatenate them, and we assume that we have a fixed size, and then go for our processing. So thank you. That was the question, and I'm done. So let's see.
Hi, so thank you, Sowmya, for your talk. It was quite informative, and I'm sure it has inspired many of us to explore NLP further. And thank you all for listening. So, we have a feedback form in the description below. It'll be very useful to us if you can kindly fill it. And have a nice rest of the day. Thank you.
Thank you, Manan.